This is another episode of BJ's Physics Classroom. We meet again today for the continuation of electrostatics. In our last meeting, we spoke about charges that are at rest. So we said that the study of charges at rest is called electrostatics. So today's discussion is going to be a continuation of electrostatics. So we begin today from quantity of charge. Quantity of charge. When we say quantity of charge, is defined as the product of current in a conductor and the time taken for the current to flow. That is what we mean by quantity of charge. So mathematically, we say that the quantity of charge, Q, is equal to IT, where I is the current and T is the time taken for the current to flow. That is what we mean by quantity of charge. The unit, the SI unit for quantity of charge is Coulomb. Coulomb, we shorten it as capital C, Coulomb. So we see that from this equation, 1 Coulomb is equal to 1 ampere times 1 second. So therefore, we define Coulomb as the quantity of charge. We define Coulomb as the quantity of charge in a conductor when a current of 1 ampere flow through the conductor for a time of 1 second. That is how we define Coulomb. Good. So take note of this equation very well. Take note of this equation very well. I'll write it when the board is dry. Good. Then we look at another term we call charge density. I'll come back to the quantity of charge density. In the previous video, I even used charge density to explain something when I was looking at how charges are distributed on a conductor. So charge density. We say Q. Well, the board is still sleeping. Charge density. Now, the charge density is given by the quantity of charge per unit area of the charge. The quantity of charge per unit surface area of the charge. That's what we mean by charge density. Take note of this equation too. What this means is that the smaller the surface area of the charge, the larger the charge density. Means that if I have a body like this, if I want to draw the charge distribution on this body, so the surface area here is small. What that means is that charges are going to be so much crowded at this area. Then, as we get to the area where we get to a place where the area is large, then you see that the charges are not so much distributed, all right? The charges are not so much crowded there. So when you compare the area here with the area here, you can see that there are so many charges here. From the charge distribution principle, charge density principle, we realize that the charge density is the quantity of charge per unit area. So the smaller the area, the higher the number of charges. The smaller the area, the higher the number of charges. The bigger the area, the smaller the number of charges. That is what we mean by charge distribution. So the formula I was talking about, Q is equal to IT. Let's call this one equation 1. Take note of this equation very well. This one and this one. So that is what we mean by charge density. Then we look at the Millikan's oil drop experiment. The Millikan's oil drop experiment. So we look at the Millikan's oil drop experiment. This is the experimental setup for the Millikan's oil drop experiment. Why the Millikan's oil drop experiment? Now, this experiment seeks to investigate the charge quantization principle, which I will take you through later after I have explained what the experimental setup is. So the charge quantization principle, that is what the Millikan's oil drop experiment seeks to investigate. Now, the charge quantization principle is basically the principle behind determining the quantity of charge on the body. That's what we mean by the charge quantization principle. So, in the Millikan's oil drop experiment, there is an oil sprayer. The function of the oil sprayer is to spray the oil and get it charged by friction. So when the oil sprayer sprays the oil drop gets charged by friction. Good. Then there is plate A and plate B. Plate A is connected to a high potential. Plate B is earthed to make sure that the potential on plate B is 0. Good. And then there's a traveling microscope that magnifies, when the oil sprayer sprays the oil, there are so many droplets coming, so the traveling microscope focuses on one of the oil drops and tries to observe that particular oil drop as it falls from plate A towards plate B. Then there is an X-ray which is made to pass through the oil drop to re-ionize the oil drop. Remember, the oil drop gets charged by friction. And quantity of charge can either be positive or negative. When the quantity of charge is positive, means you're talking about a positive charge, talking about quantity of charge of positive charges. But the quantity of charge is negative, it means that you're talking about quantity of charge for negative charges, specifically electrons. So, as the oil drop gets charged and it is falling, the X-ray is made to pass through the oil drop to change the charge of the oil drop. There was a purpose for changing the charge of the oil drop. You will know it later. Good. And then there is water bath that runs around the experimental setup, cooling and maintaining the temperature of the setup. So the function of the water bath is to maintain the temperature of the setup. So what we're saying is that the Millikan's oil drop experiment seeks to investigate the charge quantization principle, which states that the quantity of charge on a body is an integral multiple of an electronic charge, a basic charge called the electronic charge. We say the quantity of charge is an integral multiple of an electronic charge. The quantity of charge is an integral multiple of the electronic charge, where n is an integer. N is an integer which can either be positive or negative. So the formula is written as this: plus or minus Ne, where n is an integer. Now, the Millikan's oil drop experiment was performed for two purposes. One, to prove the charge quantization principle, and two, to also prove that the quantity n, which is the integer, is a whole number but not a fraction. What that means is that a quantity of charge, an electron or a proton, cannot exist in fraction. It's always a whole number. Good. So the n, which is the quantity of charge, represents the number of charges present. So when we multiply the number of charges present by the quantity, by the electronic charge, E, whose value is 1.6 times 10 raised to the power negative 19 coulombs, then that gives us the quantity of charge. For instance, if we have 1,000 electric charges there, 1,000 electrons, we multiply that 1,000 by this value, that will give us the quantity of charge on the body. That principle, that phenomenon is what we refer to as charge quantization. So Millikan performed this experiment for two purposes. For two reasons. One, to prove the charge quantization. The charge quantization principle, which is Q equals plus or minus NE, and 2. To also prove that N is a whole number, but not a fraction. N is a whole number, but not a fraction. These are the two reasons why Millikan performed his experiment. So what he did was that, in the experimental setup, he measured the distance between the two plates. The distance between the two plates, let's call that distance x. The distance between the two plates. And the traveling microscope has a timer that determines the time it takes the oil to drop from plate A to plate B. So when we divide the distance by the time, that will give us the linear velocity. All right? That will give us the speed with which the electron travels from plate A to plate B. That speed becomes the terminal velocity of the electron. All right? That speed is taken as the terminal velocity of the electron. We use the terminal velocity of the electron to calculate for the viscous force. Remember, the oil drop is falling through a viscous fluid, all right? Because the whole place is oil. So as the oil drops, there are three forces acting on the oil drop. One, the weight of the oil drop, the electrostatic force between plate A and then the oil drop. You know, the oil drop has a charge. So the electrostatic force between plate A and the oil drop, that is force number 2, and the force number 3 is the viscous force. The weight of the oil drop is mass times gravity of the oil drop. That one is easy to find. The electrostatic force on the oil drop, that one can also be found. We are yet to go there. That one is also found. So you realize that the main purpose of this experimental setup is to determine the terminal velocity, which helps him to determine the viscous force. The viscous force, F, is equal to 6 pi r eta Vt, where eta is the coefficient of viscosity of the oil. So with this, the viscous force is obtained, and then he used it to determine the quantity of charge on the oil drop. And he found out that, yes, the charge quantization principle, K is equal to NE, is true. It's correct. And then he also discovered that the N, which represents the number of charges present, is always a whole number, but not a fraction. The N is a whole number, but not a fraction. Good. So these are the two main reasons why Millikan performed his experiment. Good. Good. So later we'll look at how the quantity of charge based on an oil drop placed between two plates is calculated. It will resurface in the course of our study. So let's pick things one after the other so that when we get there, we can look at it. Good. Now we'll look at the Coulomb's law. The Coulomb's law of electrostatics states that the force of attraction or repulsion between any two charges arranged close to each other in a straight line, that force is directly proportional to the product of the charges and inversely proportional to the square of the distance between the two charges measured from the centers of the two charges. You realize that this Coulomb's law is almost the same as the Newton's universal law of gravitation. The only difference here is that the Newton's universal law of gravitation deals with the masses, and the electrostatic force, the Coulomb's law, deals with charges. So we say that, let's consider these two charges, Q1 and Q2. The two charges are placed they are separated by a distance d between the two charges. The Coulomb's force, F, we say is proportional to the product of the charges Q1 and Q2, and inversely proportional to the square of the distance between the two charges, measured from their centers. What that means is that this force is a central force, 1, because the magnitude of the force is measured from the center of the two bodies. 2, it is a field force. What that means is that the force exists within a region around a body. 3, the force is an inverse square force. The force is inversely proportional to a certain distance. So we say that the force is an inverse square force. These are some of the characteristics of electrostatic force. So when we remove this proportionality, I will introduce a constant. F is equal to K, Q1, Q2 all over D squared. The constant K is a constant which also depends on another constant. We call K the Coulomb's constant, whose value is given by 1 over 4 pi epsilon naught. Okay, 1 over 4 pi epsilon, where the epsilon, this term epsilon, is called the permittivity of the medium. Permittivity of the medium. So other characteristics. This particular force depends on the medium in which the two charges are placed. Unlike the gravitational force that is independent on the medium in which the two charges are placed, the electrostatic force, which we call the Coulomb's force, is dependent, or it depends on the medium in which the two charges are placed. And the property of the medium is the permittivity of the medium. Good. So when the medium between the two charges is air, when the medium is air, when the medium is air, then the permittivity is given by E naught. Exactly. The permittivity of the medium is given by E naught, permittivity of free space. We call it permittivity of free space, whose value is 8.9 times 10 raised to the power minus 12 farad per meter. That is the approximate value for this one. You know, so many decimal places, but this is the approximate value for this one. So when we put this value here, you know, 4 is a constant, pi is a constant, and we calculate for K. We get K to be equal to 9 times 10 raised to the power 9 Newton meter squared per Coulomb squared. This constant K, which is given by 1 over 4 pi epsilon naught. K is given by 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space, whose value is this. But we put it in, we get K to be equal to this one. This is what we call the Coulomb's constant. The Coulomb's constant. But remember, the value for K can change when the medium between the two charges also change. Take note of that. So because of that, there's another property we call relative permittivity. Relative permittivity. Relative permittivity. When we say relative permittivity, the symbol is ER. We define relative permittivity as the ratio of the permittivity of a medium to the permittivity of free space. Relative permittivity is the ratio of the permittivity of a medium to the permittivity of free space. All right? So let's make permittivity of the medium the subject, the medium in question. So we are talking about the relative permittivity of a particular medium, right? The relative permittivity of a medium is defined as the permittivity of the medium divided by the permittivity of free space. Permittivity of the medium divided by the permittivity of free space. So let's make permittivity the subject. That will give us ER E naught. ER E naught. You know, it is easy to keep the equation like this in your head so that you can always define freely relative permittivity. You can see that those ones with subscripts are put together by multiplication so that E is equal to ER E naught. You can easily remember this one. Exactly. Good. So it means that in place of this value, permittivity, we can always place this and use it to calculate for the value of K, which is the Coulomb's constant. What this means is that this force for equation 3, the force for equation 3 can be written as F is equal to Q1, Q2 all over 4 pi epsilon d squared. That is when the medium is not air, or when the medium is, when we're talking about any medium. Then we can also write it as F is equal to Q1, Q2 all over 4 pi epsilon naught d squared, where epsilon naught is the permittivity of free space. Exactly. Good. But this is the main formula. That is when we are talking about permittivity of any medium at all. Good. So take note of this equation, or this one, equation 4. You can be asked to use it to calculate for anything, to calculate for the quantity of charge at any point in time. Good. So let's look at some example. So example 1. A current of 3 ampere flow through a conductor for 6 minutes. Determine the quantity of charge that flow through the conductor, that flow in the conductor. So solution to question 1. In the question, we have been given the current I is equal to 3 ampere. We have been given the time t is equal to 6 minutes. So we convert the time t in minutes to seconds, which is 6 times 60. 1 minute is equal to 60 seconds. So therefore 6 minutes, that will give us 6 times 60. 6 is 36. That will give us 360 seconds. Good. That is the time given to us. So we say that the quantity of charge, Q, is equal to IT. Therefore, Q is equal to the quantity of charge, which is the current I, 3 times 360. And that will give us 0, 3, 6, 18, 8, 3, 3, 9, 1, 0 coulombs. It means that the quantity of charge stored is given by 1080 coulombs. It's given by 1080 coulombs. Good. Then we go to example 2. The example 2 states that 2 charges, 5 microcoulombs and minus 8 microcoulombs, are placed 10 centimeters apart in air. Calculate the force between them. Because the 2 charges, one of them is positive, the other one is negative, it means that the force between them is going to be an attractive force. So in calculation, when you have one of the charges or both charges being negative, just ignore the negative sign. The signs are only telling you whether the force will be attractive or positive. The signs, which is either negative or positive, don't play a role in the calculation, so don't bring them. Good. So we say that F is equal to K, Q1, Q2 all over D squared. Of course, the quantity of charges are given to us. So F is equal to 9 times 10 raised to the power 9 times Q1, 5 times 10 raised to the power minus 6. Remember, micro is times 10 raised to the power minus 6 times 8 times 10 raised to the power minus 6 all over 0.1 squared. We convert the 10 centimeters to meters, then we use it. So that will give us F is equal to 40 times 9 36. So that is going to give us 360 times 10 raised to the power 9, 10 raised to the power minus 6, 10 raised to the power minus 6, 10 raised to the power minus 12, 10 raised to the power 9. That will give us 10 raised to the power minus 3 divided by 0.1 squared. That will give us 1 times 10 raised to the power minus 2. All right, 0.1 squared will give us 1 times 10 raised to the power minus 2. So when this value comes up, it will give us the force F is equal to 360 times 10 raised to the power minus 1. The force F is equal to 36 newtons. It means that the force between the two charges, is given by 36 newtons. And this force is an attractive force. How? Because the quantity of charge 8 is negative and the quantity of charge 5 is positive. So when a negative charge and a positive charge come together, come closer, they attract each other. So this is how we deal with the force that exists between the two charges. So we look at another principle that we call resultant force on a charge. Here we consider charges in a straight line. Resultant force on a charge based on two or more other charges placed in a straight line. For instance, I can have three charges, Q1, Q2, and Q3, arranged in a straight line like this. Good. So I can be asked to determine the quantity, the resultant force due to Q1 and Q2 on Q1, the resultant force due to Q1 and Q3 on Q2, the resultant force due to Q1 and Q2 on Q3. Exactly. I can be asked to do this. So when I'm asked to do this, it's simple. This is how we go about it. It's simple. So let's consider the resultant force on Q1. So let's take it that these charges, this is positive, and this is negative, all right? So we have positive, and then a negative charge. We want to look at the resultant force on Q1. So to do this, we try and then, there are so many school of thoughts. Now, so we say that the charge that we are looking for the resultant force on, that charge wouldn't move. The rest of the charges are going to move. So either they move towards it for attraction or they move away from it for repulsion. So if we apply that principle to this, we are looking for the resultant force on Q1. So either Q2 and Q3 will move. Q2 and Q3 are going to move either towards it or away from it. So for instance, if we consider Q2, then we realize that because Q1 is positive and Q2 is positive, there will be a repulsion between Q1 and Q2, so Q2 will move away. So the direction of the force F between the two of them, let me call it F1, is this way. Let's consider Q1 and Q3. Between Q1 and Q3, we can see that Q3 is negative and Q1 is positive. So the force between them will be attractive force. What that means is that the force between them, F, is going to point towards Q1. So F2 is going to be like this. So when we look at these two, we realize that F1 and F2 are moving in opposite directions, so we subtract. So therefore, we say that the resultant force F is equal to F1 minus F2, where F1 is greater than F2. That is how we determine the resultant force on Q1. Good. Let me go through the same principle for the resultant force on Q2. Then, by the time I finish with the resultant force on Q3, you will get everything clear. You understand everything. So, I'm going to look for the resultant force on Q2. The resultant force on Q2. So, I'll draw them. Q1, Q2, Q3. Between Q2 and Q1 is like this. Between Q3 and Q2 is also like this. This is positive, and this is negative. That is how the charges are over here. So between this one and this one, there's going to be a repulsion. So this force, this charge is going to move away. So F1 is going to point away. Between Q1 and Q2 and Q3, the force is going to be attractive because this is negative and this is positive. So Q3 will be attracted towards Q2. So this one is going to point here, F2. Now we realize that the two forces are pointing in the same direction, so we add them. Therefore, the force F becomes equal to F1 plus F2. F1 plus F2, like this. We are looking for the resultant force on Q2. So this charge, will it move away or to move closer? Because of positive, there's a repulsion, so this one will move away. Because of positive, negative, between this charge and this charge, this one will move towards it. This way. So the two forces are pointing in the same direction, so we add them. The last one, resultant force on Q3. we are looking for the resultant force on Q3. So we sketch them Q1, Q2, and Q3. Between Q1 and Q3, is like this, and between Q2 and Q3 is like this. So let's look at the direction of the forces. This charge is positive, this charge is positive, and this is negative. So between Q1 and Q3, there will be attraction. Q1 and Q3, attraction. So the force, this charge will be dragged towards this one. So the force is in this direction, Fy. Between Q2 and Q3, there will also be attraction because positive, negative. So this one will also be attracted towards this one like this. So F2 will also point here. Now we can see that both F1 and F2 are in the same direction. So the resultant force, F is equal to F1 plus F2. Good. So that is how we determine the resultant force on charges. Thank you very much for being part of today's episode of the BJ's Physics Classroom. Like I always say, if you haven't subscribed to my YouTube channel, please subscribe to the channel. The channel is BJ Online, and you can also visit my website bjonline.com for anything physics that you want over there. And then you can also visit my Facebook page, BJ Online on Facebook. The Facebook page is BJ Physics Classroom. Thank you very much. Till I come your way again for a continuation of electrostatics, where we'll be dealing with electric field and electric field intensity. Thank you very much. It's your man BJ. Bye bye.